Today what we're going to work on is deriving the derivatives of the trig functions. And I'm also going to find my eraser. That's kind of a first key step. So, derivatives of trig functions. Now remember, we've already talked about the derivatives of polynomials, and we've talked about the derivatives of exponential functions to some degree, although really we've only done e to the x at this point. But before we move on to figuring out other exponential functions, we'll deal with these trig functions. And I want to start off by looking at what is the derivative of sine x? And then we're going to look at the derivative of cosine x, because it turns out that when you do the derivative of sine x and cosine x, well, all of the other trig functions are defined in terms of sine of x and cosine of x. So once we have those, we can figure out the other four trig functions from that. Now, if I want to do the derivative of sine x, I'm going to start this by going ahead and using the limit definition of the derivative. So we have the limit as h goes to 0, sine x plus h minus sine x divided by h. Now, here is where we need to use a little bit of a trick. We need to use the sum identity to split this up. So this is going to become equal to the limit as h goes to 0 of, excuse me. So let me make sure I have this correct. We're going to have sine x cos h. And then we have plus cos x sine of h. And then we're going to have minus sine x, of course, divided by h. So, here's what we're going to end up with then. As h goes to 0, because the trig functions are continuous, cosine h is approaching 1. And that means that this sine x times cosine h is approaching sine of x. So sine x minus sine x, this is going to 0. So that part is something that we're going to be able to deal with in a moment. Actually, let me rewrite this as we do, because we have to be very careful about this. So this is going to be the limit as h goes to 0 of sine x times cosine of h minus 1 divided by h. And then we're going to have plus cosine x times sine of h divided by h. So there we go. Now, the thing that we're going to have to work out then is what happens in the limit as h goes to 0 with this term here, and then what happens to this limit, this sine h, sorry, that h does not look very h-like, this limit of sine h over h as h goes to 0. Well, it turns out we can pretty much fix this just by looking at this one. Once we figure out the limit as sine h over h goes to 0, the limit for the 1 over cosine is going to be relatively straightforward to figure out. Okay, so I wouldn't say necessarily immediately obvious, but it is going to be somewhat straightforward. So keep this thing in mind here, and we're going to now try to work out what is the limit as h goes to 0 of sine h over h. I'm also going to knock everything off on my desk, but we'll worry about that later. So the limit as h goes to 0 of sine of h divided by h. Now, let's first of all try to get an intuition for what this should be. It's not actually very easy to see, but if you think about the definition of the sine of an angle in terms of the unit circle, right? We have the unit circle here. I'm just going to draw the right-hand side. We have some angle H. Now, the sine of H is the height of this triangle. And if the angle is very, very small, then the height is almost exactly the same as the arc length here, which is the angle. The angle is the arc length if we're measuring this in radians. And so that means that sine H and H are very, very close to each other. And so we might expect that this ratio ought to approach 1. But how do we actually go ahead and prove that it is equal to 1? Well, the proof is a little bit involved. In order to do the proof, we are going to need to look at some geometry stuff. So let's take a look at some geometric constructions here. And you're going to have to remember a bunch of trig and some basic things about radians. So here's the construction that I want to look at. And we're going to consider the case where H is bigger than 0. So we're really looking at the limit from the right. The limit from the left, though, it's pretty obvious that it has to be the same. Why does it suffice to look at the limit from the right-hand side? Well, the reason is because sine of negative H over negative H is equal to sine of H over H, because these are both odd functions. And therefore, the limit from the right is going to be the same as the limit from the left. So if we take the limit as H goes to 0, it doesn't matter if we're doing it from the right or from the left, they have to be the same. So therefore, it suffices to consider H positive. And that's going to make my constructions just more straightforward to do. I mean, we could do the constructions for negative H's as well, but this makes it easier. So let's think about the unit circle here. And we will think about an angle of H. We will think about this triangle, which has a height of sine H. And then we will also think about this triangle here, which has a bottom length of 1 and a height here of tangent of H. Why is it the tangent of H? Well, it's the opposite over the adjacent, and so if the adjacent side is equal to 1, then this is just 1 times tangent of H, so this height is tangent H. Now, I'm going to erase this for the moment. I don't really want to, because we do need to come back to this in a bit, but make sure you have this written down, because we are going to need to come back to it momentarily. So at this point, what we could say is the area of the small triangle is less than or equal to the area of the wedge, the pie-shaped wedge here, which is less than or equal to the large triangle. So notice here that I've actually got these 3 different things here combined, okay? We have the small triangle, the wedge, and then the large triangle. And their areas have to be in this order because each one is contained in the next one. The small triangle is inside the wedge, and the wedge is inside the big triangle. So let's now write down the areas of each of these things. The area of the small triangle is going to be 1/2 base times height, which is 1 times the sine of H. The area of the wedge is going to be 1/2 times the radius squared times the angle in radians, which is H. And then the radius of the area of the big triangle is going to be 1 times tangent H times 1/2. So this is 1/2, 1 times tangent of H, which is really sine of H divided by cosine of H. So now what we can do is, now that we have got this inequality going here, and I'm going to erase this because at this point we are literally just working with this inequality. What we can say is 1/2 times sine of h is less than or equal to 1/2 h, which is less than or equal to 1/2 sine of h over cosine of h. And I can multiply through by the 1/2 to get rid of it. So I have sine of h is less than or equal to h, less than or equal to sine of h divided by cosine of h. So now what do I want to do at this point? I want to divide everything by sine of h. So I'm going to have 1 is less than or equal to h over sine of h, less than or equal to 1 over cosine of h. So I divided everything through by sine of h, and because h is positive, sine of h is also positive, and so I get this inequality. Now, I'm not actually interested in h divided by sine of h. I'm interested in the reciprocal of this. But I can take the reciprocals of each of these things and it just flips the inequality. So I get that the cosine of h is less than or equal to sine of h over h, less than or equal to 1. So think for a moment about why I can take the reciprocals here and just flip the inequalities. It has to do with the fact that everything here is bigger than 1, or well, bigger than or equal to 1. So when you take the reciprocals, their sizes just get flipped around the other way. And now, what we know is that from the squeeze theorem, the limit as h goes to 0 of cosine of h is less than or equal to the limit as h goes to 0 sine of h divided by h, which is less than or equal to the limit as h goes to 0 of 1. However, cosine is continuous, so this is equal to 1, because the cosine of 0 is 1. And 1 is a constant, so this is also equal to 1. Therefore, this limit is equal to 1 as well. And that is exactly what we kind of said we sort of expected. We expected that this limit would be equal to 1. So now we also need to figure out, what about that, let's write down what we found here. This limit is equal to 1. So now we have to ask, what about the limit as h approaches 0 of cosine of h minus 1 divided by h? Well, this one is going to require us to be a little bit more clever here. So to do this, I'm going to multiply on the top and the bottom by cosine of h plus 1. This gives me the limit as h goes to 0 of cosine squared h minus 1 divided by the cosine of h plus 1, all multiplied by h. And this is going to be the limit as h approaches 0 of negative sine squared h divided by cosine of h plus 1 times h. Okay, now, why did I think to do this? Well, when I see something like this, I sort of think about, what could I do that would be like rationalization to maybe get something that is more easily handled? See, if you multiply by this, it gives me something in terms of sine squared. Why do I want it in terms of sine squared? Well, because I already know something about the limit of sine h over h. See, at this point, what we can do is we can take this limit and we can turn this into the limit as h approaches 0 of negative sine of h divided by cosine of h plus 1 times sine of h divided by h. But now, this approaches 1, this approaches 0, so this limit comes out to be 0. Well, that's actually a really nice result. That part just goes away entirely. So, remember what we were trying to do back at the start was to actually figure out the derivative of sine. Go back and plug in. We just figured out that the limit of sine h over h is equal to 1, and we just showed that the limit as h goes to 0 of cosine of h minus 1 over h is equal to 0. So go back and plug these into that formula that I erased before, and you will see that what we just found is that the derivative of sine x is going to be equal to sine x times 0 plus cosine x times 1, which is actually just equal to the cosine of x. That is a really beautiful and nice result. Intuitively, this also makes a lot of sense for reasons that you'll get into later that come down to the tangent lines to circles. But yeah, it does turn out that this is really quite sensible and sort of what we would expect. So what about the derivative of cosine? Well, the derivative of cosine is actually really, really similar. The derivative of cosine x, this is going to be equal to the limit as h approaches 0. And then we're going to have cosine x plus h minus cosine of x divided by h. Oh, excuse me for one moment here. I'm so sorry. Sorry about that. So we are back. So what I want to do is I want to then rewrite this by using the sum identity for cosine. And when I do the sum identity for cosine, I get something kind of similar to what we did for sine, except, well, there's a few little minor differences. So we actually get cosine of x times cosine of h minus sine of x times sine of h. And then, of course, we are subtracting cosine x still. So this is going to become the limit as h approaches 0. If I rewrite this a bit, this is going to be cosine x times cosine of h minus 1 over h minus sine x times sine of h divided by h. So notice we've now got to deal with the same two limits as we did in the case for sine x. Well, we already figured out what those are, so we're actually kind of all set with this. And we see that this is 0 and this is 1. And therefore, this comes out to be negative sine x. So there we go. We have just derived the derivatives here of sine x and cosine x. And there's actually a very nice pattern here because you'll notice that if f of x is equal to sine x, then f prime of x is cosine x. F double prime of x is equal to then negative sine x. F triple prime of x is going to then become negative cosine x. And the fourth derivative of x is going to come back to being sine x again. So we actually get this cycle in cycles of 4. You start off with, you can think of this as level 0. It starts with sine x. At level 1, you're at cosine x. At 2, negative sine x. At 3, negative cosine x. And at 4, you come back to the same. So we can actually use this trick to very quickly find high-level derivatives. For example, let's suppose that I wanted to find what is f of 53 of x. In other words, the 53rd derivative. Well, all I have to do is I need to ask, what is the remainder of 53 divided by 4. Well, 53 divided by 4, this is 52 with a remainder of 1. I'm sorry, what am I saying? 52. It is 13 with a remainder of 1. The important thing is that 13. 52 is divisible by 4. So if you do 52 derivatives, if you do any number of derivatives that's divisible by 4, you will get back to where you started. If you do one more, you will get to cosine of x. So the 53rd derivative of x in this case is equal to cosine x. The same sort of thing applies if we started with a cosine. So if I had something where I said, okay, g of x is equal to cosine x, then the first derivative is going to be negative sine x. Second derivative is going to be negative cosine x. Third derivative is going to be equal to positive sine x. And the fourth derivative is going to come back to being positive cosine x. So I want you to take a moment here and see if you can figure out what is the, let's do the 31st derivative of x. So pause this for a moment and see if you can think of what that would be. Well, the answer is, what is the remainder when I do 31 divided by 4? This has a remainder of 3. So if you do 28 derivatives, you end up back where you start, and then you have to do 3 more derivatives. So that would go 1, 2, 3, and we end up with sine x. So the fact that they follow this cyclic pattern in cycles of 4 is really quite nice here. Now, we can use what we have said so far together with the other rules we've had before as well. So for example, let's suppose that I wanted to do the derivative of x cosine x. Well, what I can do is I can say, okay, my f is going to be x and my g is going to be cosine x. That makes f prime into 1 and g prime into negative sine x. So if I do f prime g, this becomes 1 times cosine x plus f times g prime. That's going to be x times negative sine x. And we end up with cosine x minus x sine x. So we can use the product rule to do these kinds of derivatives just as we would with any other functions. We can also use the quotient rule just like we would with any other functions, okay? So for instance, if I had something like take the derivative of sine x divided by e to the x, well, I can say my f here is sine x, which makes my f prime into cosine x, and g is e to the x, which makes g prime e to the x as well. And then using the quotient rule, we have fg prime minus gf prime. Sorry, f prime g minus gf prime. I got the signs wrong in my head. That's where I was pausing for a second. So f prime times g, that's e to the x cosine x, minus fg prime, that's e to the x sine x, divided by g squared, which is e to the 2x. But of course, you can cancel out an e to the x here, and you are left with cos x minus sine x divided by e to the x. So you can use the quotient rule just as you would in any other situation. Now, using the quotient rule actually allows us to do more than just these kinds of things. It also allows us to find the other 4 trigonometric functions derivatives, okay? Because what can I do to find, let's say, the derivative of tangent x? Well, this is going to be the derivative of sine x divided by cosine x. So take a minute and see if you can work out for yourselves what this comes out to be. All right, so let's take a look at how this works. We have f is equal to sine x, g is equal to cosine x, f prime then becomes cos x, and g prime is negative sine x. So if we do f prime times g, this is going to be cosine x times cosine x. That's cosine squared x. Then we have to subtract fg prime. That actually becomes plus sine squared x. And we have to divide by the denominator squared, which is cosine squared x. Well, cosine squared x plus sine squared x, this is just 1 over cosine squared x. And that is actually secant squared x, if you remember your definitions of your trig functions. So there we go. The derivative of tangent is secant squared. Well, what about the others? Cotangent works out really, really similarly. So if I want to do the derivative of cotangent, take a moment to see if you can work this out for yourselves before you watch me do it. So I want you to actually think about this for a minute first, because now that you've seen how to do tangent, this is really similar and you might be able to work it out. But let me just show you how you can think about this. This is cos x over sine x. So we're going to take f equals cosine x, f prime is then negative sine x, g is sine x, g prime is cosine x, and this almost works out the same, except we end up with our things a little bit different. So f prime times g is negative sine squared x. Then we have to subtract f times g prime, which is cosine squared x, and in the denominator we get sine squared x. Well, this is actually negative 1 over sine squared x, which is negative cosecant squared x. So the derivative of cotangent is negative cosecant squared. As I said, very similar to the tangent. We work it out the same way, but we do pick up this negative sign. And then you can work out your derivatives for secant and for cosecant. So if I wanted to do the derivative of cosecant x, this is the derivative of 1 over sine x. So I can say, well, f is equal to 1, g is equal to sine x. F prime is 0, g prime is cosine x. So f prime g is just 0 times sine x. And then I'm going to be subtracting f times g prime, so that's minus cosine x. And in the denominator, I'm going to have sine squared x. So this is 1 over sine x times cosine x over sine x. Negative 1 over sine x times cosine x over sine x. This is going to be negative cosecant x cotangent x. What about secant? Well, secant works out almost the same way, except we're going to end up not picking up a negative, and we're working with tangents and secants instead of cotangents and cosecants. So derivative of secant of x, this is going to be the derivative of 1 over cosine x. F equals 1, f prime equals 0, g equals cos x, g prime equals negative sine x. So my derivative is going to be 0 times cosine x plus sine x divided by cosine squared x. So this is going to become 1 over cosine x times sine x over cosine x, which is secant x tangent x. So once we had those derivatives for sines and cosines, everything else we were able to find by just applying the quotient rule and the definitions of the trig functions. So this kind of shows us one of the ways in which these rules are really, really powerful, okay? And where we can end up using these all over the place, not just to solve like random problems, but to really discover important new derivatives and things like that. Now keep in mind, you can use these 6 trig derivatives in combination with any of those rules. So if I have a secant x multiplied by something, well, I can just use the product rule, and then I can use the fact that the derivative of secant is secant times tangent. Or maybe I have a cosecant and it's divided by something. Well, I just use the quotient rule together with what we found for the derivative of cosecant. So it works out the same sort of way. Now, what we're going to want to move on to doing next is we're going to start looking at what happens when you take the derivative of functions that are composed together. And once we see that, which is going to give us another important rule, then I'm going to start like showing you just a bunch of random examples of derivatives and how you can use these different rules to work them out. But for now, hopefully everybody's okay with this stuff that we did here, and keep practicing things, and we will move on to, like I said, next time we'll be talking about what you do when you've got function composition inside of your derivatives.